All right, we're going to start here with a little bit of chi-square analysis. Um, like I said, this is part 2 of the PowerPoints for week 3. And we're going to start with this idea of a null hypothesis and an alternative hypothesis. Or you can think of it as a hypothesis and a null. There are lots of terms, and it can be done in many different ways. But you usually have two hypotheses. And usually you use them in such a way as to so that they fit your type of analysis. And we're doing chi-square. So what we're doing is we're comparing two groups. And I discussed this before. And essentially what we're doing, one of these needs to say that no difference exists between the groups. The other one says, yes, there is a difference between these groups. And so that's what we're saying here, is that the null says that there is no difference in between the proportions of your group. Oop, went back. And then the alternative is that yes, there is a difference in the proportions. So as I said before, maybe you have a ratio of flies of here it's 3 to 1. And then the alternative is no, that the ratio really isn't 3 to 1, it's something else. And then you do your chi-squared. And your chi-squared, you have your observations, and your observations are kind of close to 3 to 1, all right, but they're not quite 3 to 1. But how do you know if it's too far away for you to say it's not? In other words, it's okay for it to be a little off, but it's not okay for it to be a lot off. When do you go from it being okay to be a little off and you still consider it the same ratio, and when do you make your decision to say no, that's too big? That's what chi-square does for you. Chi-square says that 2.9 to 1.1 is okay, but 2.5 to 1.5, no, that's too big of a difference. That's not close enough to 3 to 1 for me to accept that we have the right model. So you do have to understand also there's something called the degree of freedom. And the degrees of freedom, the best way to do it is just understand how to calculate it. It's the number of classes you have minus 1. So what in the world are classes? Well, in the P experiment, classes are the types of P's. So you have purple and you have white. So that's 2 classes. So 2 minus 1 is 1. If I had 4 different colors of P's, it would be 4 minus 1. Most of the time, we're either going to have 2 types or 3 types, and you're going to subtract 1 from it. So your degrees of freedom, depending on the number of types you have, in other words, maybe homozygous and heterozygous, or if those each have a different phenotype, or if you're talking genotype, it could be. So it's homozygous, heterozygous, homozygous dominant, heterozygous, and homozygous recessive might be your 3 types. So you might have as many as 3, minus 1 would be 2 degrees of freedom, or you might have 2 in this case, and minus 1, and that's 1 degree of freedom. All right, and when you do that, that tells you the size of your table. All right, so your table has to be at least a 2 by 2 because it's degrees of freedom is the number of rows minus 1 times the number of columns minus 1. Right? And that's all determined by the it's not going to the next one again. There we go. Coin toss. All right, so this is the simplest one because they're just 2 and it's a ratio of 1 to 1. You think that there's going to be an equal number of heads and tails, so it is a very simple version of the chi-squared. So either the coin is fair and you get something close to 1 to 1, or it's not fair and you get one of them being very biased, and you roll ahead more often than you do tails quite often, and that would be the alternative hypothesis. All right. And here's how you determine your degree of freedom. There were two choices, heads or tails. -1 is 1. All right. Here we have to wait a second on our... Let me see if I can go to... It's just slow. I don't think that's the end of it. It's not. Okay, so what would we do if we get this? I'm just going to have to go to the regular PowerPoints here. Well, we expect, of course, what? 50-50. So heads and tails, and our expected is 50-50. Expected is your model. If everything works out perfect, it's just the way the theory says it should work, you should get, out of 100 flips, you should get 50 heads and 50 tails. But in observed, when you flip it, you get 60 heads and 40 tails. So you use this formula. All right, now the expected is E, the observed is O. So these are the ones that you actually flipped. These are the ones you did not flip. You just say that's what it should be. So your E is like 50 here and 50 here. So 50, 50, 50, 50. All right, and then 60, 40. We have to put in one for heads and one's for tails. So we do chi-squared twice. We do 60 minus 50 squared over 50 plus 40 minus 50 squared, 50. And so we do this. We add those together. That's what the summation does. It says do this twice. All right, we had 60 and we have 40. So we're going to use this formula. That's what the E means. Do this formula for however many variables you have here. We have one for 60 and one for 40. We're going to add those together. The summation means sum them all together. All right, and we end up with 4. So, okay, we have an answer of 4. How do we know if that's our answer, but how do we know this is too much of a difference or too small of a difference to say that 60-40 is the same as 50-50 given the size of our sample? Well, how do we know that? Well, we go to a table. And how many degrees of freedom we had? We had 1. All right, and then we get a choice. How accurate, or should I say precise, do we want to be? If we want to be right 95 out of 100 times, we would go to the 0.05, because the 0.05, this is how often you're wrong. So think of it this number. I'm wrong essentially 5% of the time. All right, that's kind of what you're saying here. And if I'm willing to accept that rate of being wrong, the number is 3.841. All right, and that means the critical point is p.05, and that's the one we will use in this class. It's an acceptable one used all across science and specifically in biology. Sometimes you'll go to 0.1, but that 10% being wrong 10% of the time, but that's not very common. You usually want to go here or better. All right. I'm sorry. Here, this is. Let's just leave it at this. I think I said that backwards. So we're just going to say we're going to go here, and this is where we're going to stick throughout this class. And we're going to say here is our number because our degrees of freedom are 1, and our magic number, I call it that, the magic number is 3.841. And so if you go over, all right, 3.841, well, that means you are quite a bit off. All right, and you have to reject this group of this sample as being part of the bigger group, of being the model. So if you're over this magic number right here, 3.841, you have to say that we reject the null hypothesis, and that's really the way you should say it. You reject the null. You shouldn't say accept. You shouldn't say you proved anything. You just say that you've rejected the null hypothesis. And that's what it has. The red here means we're over 3.41, so we're on this side and we reject the null. If, however, we were under 3.841, so our number came up at 3.6, then we would fail to reject. All right? Doesn't mean we accept. Some places you can say accept, but we fail to reject the null. So that means the null is still a possibility. It's it may not be likely, but we are still within the realm of possibilities that this set of data is part of follows the guidelines set down by our model. Our model says it should be 50-50. We're a little off, but we're not so far off that we're going to just outright reject this data. So this data gets to stay in our pool of data where we say that this data is following our model. All right, that's kind of the way you think about it. So the idea here is our magic number is 3.841, and it will be pretty much for almost everything. You might go up to 5.991 if we did 2 degrees of freedom, but these are probably the only two you'll have to use in this course. Though I wouldn't put it past Dr. O'Brien to have you be able to read this this chart and be able to understand that as you change your degrees of freedom, you move up and down, and as you change your critical value, how stringent do you want to be? You could move in this direction as well. So keep in mind what these do, what it means to move back and forth here, left and right, and what it means to move up and down. So you need to be aware of that. So remember, if you go above this number, you're saying that no, we can't accept our model. All right, we're gonna our model being the null hypothesis, we're gonna reject the null. So just keep in mind, and the wording can be so poor sometimes in this, and it's different in different studies. Just be aware, in the wording on this particular one, we had a null hypothesis and an alternative hypothesis, and you have to be clear on which one is saying your ratio is the same as the model and which one is saying it's different than the model. All right, and if you remember up here, what was it? Here we're saying the null is the same, and the alternative is that our proportion is not the same. It's not 1-to-1. So keep in mind what HO and HA say. All right, moving on a little bit more. Here it's much more difficult because we have a ratio of what? We have how many? 1, 2, 3, 4, 5, 6 different. Like if this were flowers, you'd have 6 different colors of flowers that you could be. And so, of course, if you have 6 different possible outcomes, like instead of just purple and white, if instead you had 1 through 6 on a die, it would be, you would start with 6 and then -1 gives you 5 degrees of freedom. So if you go back on 5 degrees of freedom, that would be looking down here. If we were at the same critical value, if we use the same critical point, we would be here at 11.07. That means we could go a lot higher and still not reject the null. Be careful. The wording will just drive you crazy here. It's one of the reasons this is considered difficult, is because you have to be very clear on the wording. All right, and yes, as you can see, they show just like I did, 11.07 is where you would go. Now up here we just have 2 flowers, so it's only 2 degrees of freedom, purple and white, and we have 3 trials. All right, so we're going to do a chi-square with this trial, a chi-square with this trial, and a chi-square with this trial, and then we're going to sum them up. All right, so here on the first one, it's 1.33, and remember our main number is 3.841. So this one is definitely below 3.841, but the second one is not. So this one or x3, sorry. This one fails. These two are great. This one is below 3.841, and this one is 0. The way you look at it, if these numbers come out the same, 300, 100, 300, 100, that means they're following the model exactly, and chi-square is 0. So think of it this way. 0 is perfect. It means you aren't just close to the model, you are right on the model. You are getting exactly what you predicted. There is no variance in the numbers. All right, so as we said here, fail to reject with the first 2, especially the second one where it was 0, but the third one we had to reject. All right. I want to do a whole different PowerPoint on balancers, so I'm going to skip this one and come back to balancers later in the week. So there are lots of pictures here, and I will start with this one, but I'm going to add this to another video, all right? And we'll do balancers separately.